by SAULO Oliveira. He got his PhD in applied math from University of Colorado at Denver, and now he's a faculty of the math department of Federal University of Paraná here in Brazil.
Okay, thank you, Claudio. Thank you also, Alexei, and the organizing committee for inviting me to this meeting. Actually, I think you mentioned about the last lecture. It would be kind of a lecture, this presentation. This is a joint work with some people from the National Lab for Scientific Computing, close to here, Petropolis, and Christian Moen and Lee from Lorraine. I was involved in a small part of this work regarding one particular step of a numerical method. I would just talk a little bit about the whole thing during the talk about this multi-scale, this two-scale model for expanding expansive porous media. And in the beginning, I would try to explain the idea behind the discretization that we use for this, for dealing with the non-local terms that will arise from this model. So let us start with this very simple, let's say, toy problem. I'm going to consider a 1D nonlinear integral equation. So there's even a little small intersection with the Amoris talk, the last talk. So we have we want to solve this equation for you. We have this compact operator, this integral operator here, where this kernel. I'm going to assume a little more regularity. Later I will drop this regularity, but now just let us say that this is a continuous kernel, and we want to figure out what is this function u here. So we have this nonlinearity from this function f. The function g is, let's say, is a source, is an input data, and let us discretize this domain in n+1 point. Consider like the finite element classic functions, piecewise Lagrange polynomials, and take a very simple algorithm to solve this equation, the collocation method. We want to find a function expanded by this piecewise linear functions, such that this equation is satisfied pointwise. That's what I'm asking for, continuity. So being now a linear problem, let's say a linear approximation, let us just plug in these linear combinations. Use the fact that this operator is linear and have the sum outside. Unfortunately, we cannot drop the sum out of the f. So that's how far we can get. And use the fact that these functions are nodal functions, so this will be 0 or 1 depending on x, and j, and y. So now we have this algebraic problem. Let's say vector. Now we want to find the vector u, the weights of the linear combinations that satisfy the system of nonlinear equations. So in vector form, that's what we have. U equals T1 of y, where T1 is f of this operator. Now we can see this as a matrix times u plus g. G is the function evaluated at each of these points. Just to have an idea of how this matrix can look like, let us use the trapezoidal rule to evaluate these integrals. So we want to approximate this integration on y by weighted sum. And again, if we use this weighting points as the same points of our collocation scheme, this will reduce to just xy, xj. So this matrix, in the end, this matrix K tilde here, for this particular discretization, will be nothing but the kernel evaluated at the collocation points. So it's a very simple scheme times the trapezoidal weights. So that's how it would look like in this simple discretization. And if we also have, this is another assumption, if we have that this kernel is invertible, if the original, if the continuous, you can get this also from the continuous, if the continuous kernel is invertible as well, then we can do a little trick to move the k out of the f. So instead of solving for u, we solve for v being equals k times u. So u becomes k inverse v, k inverse u becomes v, and then we move k tilde to the left-hand side. So we have this very nice scheme where we have, let's say, the non-local term out of the nonlinear term is a nice split of the two difficulties of this problem, which is the nonlinearity and the non-local character. So that's how it would look like. And both schemes, it's not always that we can do this if we either using this scheme or that one. This call us to use a fixed point iteration, a Picard iteration. It's a very natural choice, the way it's set up, the way it's written. And then we can just iterate this in this fashion. That's the approach we actually originally used. We did a spectral decomposition of our nonlinear, non-local operator, kappa of x, k of x. We consider another parallel, an auxiliary and parallel problem, where we want to find eigenvalues and eigenfunctions for this operator. And we can actually solve in the same fashion. We try to find a linear combination of piecewise constant functions satisfying this eigenvalue problem pointwise. And then we have a discrete eigenvalue problem where the weights, the numbers that define the linear combination of our eigenfunctions are actually an eigenvector for this linear system, this eigenvalue problem involving the same matrix, k tilde. So that's a different way to see the problem. That's also in connection with the former talk, if k is a compact operator, it can be shown also in the discrete level that these functions here, these eigenfunctions, psi, they are linearly independent, so they can be used as a basis instead of our original Lagrange basis. So that's the idea we used. Let's just see a little bit of connection between both approaches. We now substituting a linear combination of the psi functions inside the collocation method. Here we use the fact that they are eigenfunction of this operator, so that the part inside the F will simplify. And in vector form, that's how this would look like. Where now we have a matrix with the diagonal of the eigenvalues, and V is are the eigenfunctions over the collocation points. And again, if the operator is invertible, that is, if the eigenvalues are non-zero, we can do a similar transformation to recover. To move out the V and D from the nonlinear part, and that's what we find. So in this matrix here, exactly, let's say the matrix G is equivalent to the matrix K, the original matrix. So that's actually K tilde. So that's where that's when both methods connect themselves. So this approach, we think it can be useful if we need to find the eigenfunctions and eigenvalues with the Galerkin method instead of the collocation method. And in this sense, we may consider now a L2 kernel, no longer a continuous kernel. And in situations they are not so frequent. I'm afraid they're not so frequent in the problems that we are dealing. If we have the eigenpairs, we can use them as this information. The example will give an idea of how can we use the exact eigenpairs. So I want to choose the function g. Well, it is not shown. Let's go back a little bit. So I want to choose this function g in order that cosine of 4 pi x is the solution of the problem, fx squared, and that's our kernel. This kernel has we know the eigenvalues and eigenfunctions for it. So we can use the exact information of the spectral decomposition. Let us run the Picard iteration, the fixed point iteration, starting with the function 0, this function here in blue. Here's the exact solution, this is the error. So here we have the collocation problem, collocation method, and the collocation using the spectral decomposition using the exact eigenpairs. So after one step, the error drops a lot for both methods. Another step, so now we're about 10 to the 7, 10 to the 8, and by then the solution has already converged. So we have a little bit of an advantage. It's not that significant, from 10 to the minus 7 to 10 to the minus 8. If we have the exact eigenpairs, just to give an illustration of what can we have. And now let's move to the main motivation of this problem, the model for expansive porous media. Let's think of a macro domain which is periodically divided in small domains. In each cell, each domain will be divided. We have a fluid and a solid phase. Okay, so that's the domain, our pore scale. And so this is just an overview of the problem. We want to find the total stress and the displacement in the macro scale. So here's some of the information. This is information in the system. We have the pressure of the bulk fluid. The stress is defined in terms of these auxiliary quantities by Liouville's coefficient and some average modules, average tensors. And each of them in turn depend on some more coefficients. Sorry for it's getting more and more information here. So we have some information. I'll just go a little quicker. Some parameters that were determined in this model. And some of these quantities are local quantities that we want to set up with equations in the pore level. So that's where I want to arrive in. So we have these equations for the ions correlation, for equivalent the stress in the cell, and these are some canonical problems that show up in the analysis. And we want to focus in this part here of the problem. So we have this equation for the electric potential plus the ions correlation. So we want to solve for phi. So these are our unknowns, phi and j. So this is a system with as many equations, as many unknowns as the species we have for the ions. So here's some more information. What makes special this scheme is the presence of this correlation term here. It comes from the mean square approximation, and that makes this problem non-local and gives some more information with respect to the Poisson-Boltzmann. We just see it a little bit more time. And in the particular case that we're going to see, just this is more an illustration. We look in the special case of two species, ions with similar valences, symmetric valences. So the equation reduced to now two equations for the ions correlation. And let us rewrite this a little bit more. It should be, yes. So also have this normalization, this dimensionless potential. And just a little manipulation. Let me go back a little bit. I want to split from our correlation functions. I want to split this part, this dependence, and then write them separately here. So now we can start writing the schemes, the numerical schemes to solve these equations. We want here, let's say, a delay between this part of the solution, this part of the ions correlation and the integral part, so we can deal, so we can avoid problems with this Neumann boundary condition here, and we can solve in the staggered manner, in the sequential manner, these two systems. One will be feeding the others, and both of them are nonlinear systems. For the first system, for the electric potential, I'm going to use the Galerki method and the Newton method to iterate. And here is where the simple method in the beginning shows up. So this is our, now we have a system of nonlinear, that's where the nonlinearity takes place, of nonlinear integral equations, and that's where we're going to use the method I outlined it for you in the beginning. Just a few words on the numerical experiments. This is the geometry where you solve this with a 2D arrangement. So that's the solid phase, and here the fluid phase. The results for the ions correlation will be compared just to check the consistency with the classical Poisson-Boltzmann problem, where we don't have we don't have the correlation function, we don't have the integral term here. So that's how they look like. Here in this slide, the next, we're changing the relative height, the relative sizes of the dimensions in the x and y directions with respect to the particle sizes. So here the relation 6.4 B is horizontal. So horizontal, disproportional horizontal 6.4, on the vertical 1.6. So these are, the green ones are the non-local results, and these are Poisson-Boltzmann. And now changing for these proportions now. So for when the dimensions are a little bit higher than before, both models, Poisson, Boltzmann, local, let's say local, and the non-local have a very high similarity. So these are the ideas that were involved in the solutions. That's, of course, there's a much longer, much bigger algorithm. That's just one small part of it. What I just wanted to show you today is about this part of the collocation method. This step, what I did was to choose a special set of basis functions that we found from solving that auxiliary eigenproblem I showed in the beginning. And some details I didn't tell you. The kernel, the mean spherical approximation kernel, when we move it to the rectangular arrangements, in the end we have a kernel that has some logarithm singularities. They need to be regularized. But perhaps using, as I mentioned beginning, perhaps using the Galerki method and trying to have a better, dealing a little bit better with the singularities, perhaps we can solve the problem without regularization, just use the plain Galerki method to solve, to separately find our bases and solve the collocation without having to change without approximating our data. So that's what I wanted to present. Thank you for your attention.
Questions?